So, what is a permutation? Well, let's check out this one. For this one, you guys choose a card from the ace pile and keep it. Most of the time when things happen like this, they say that it's without replacement. Okay, and I don't know, I just kind of want you guys to get used to that vocabulary, but keeping it is without replacement. So you choose a card from the ace pile and you keep it, and then you choose another card from the ace pile. List all the possibilities. So I have to do this. I have to list the possibilities so you guys see it. If you choose the ace of hearts first, what else can you choose? Like what could else? Like you choose the ace of hearts, and then you choose again. You could get the ace of spades, and then you could also get the ace of clubs, and then you could also get what? Ace of diamonds. Whoa, that was going to be a D right there. Okay, and then let's say you start over, and this time instead of getting the ace of hearts, you get the ace of spades. And then, well, what can you get if you choose the ace of spades? Ace of what? Hearts. Then we have the ace of spades and the ace of diamonds. And what am I missing here? So ace of clubs. Oh, continuing on with this never-ending process. Ace of diamonds, ace of diamonds, ace of diamonds, because there's three other aces. The ace of hearts, the ace of spades, and the ace of clubs. Okay, last one, and then we get to move on from this. We have the ace of, what have I not done yet? Clubs. Okay, the ace of clubs, ace of clubs, ace of clubs. And we have ace of hearts, ace of spades, and last, ace of diamonds. Now, I know, like, this, I wonder if some of you guys noticed this. We have the ace of hearts and the ace of spades right there. And then over here we have the ace of spades and ace of hearts. But we still count them as separate outcomes, because here the order matters. Order is important here. If you choose the ace of hearts first and then the ace of spades second, that's different than choosing the ace of spades first and the ace of hearts second. So you have to count them twice. So in order to do this one, what's our counting principle look like? Well, we have our first event. That's when we choose our first ace. For our first event, we'll call it E1 for our first event. For our first event, how many choices are there when we make our first choice? There's 4. Okay, and then for our second event, we'll call that E2 with my cool little tray looking thing there. How many choices do you have for the second choice? You have 3. And the counting principle says that if you multiply the two number of choices, you'll get the total number of outcomes, which actually works out because there's 1, 2, 3, 4 groups of 3, and 3 times 12, or 3 times 4 is 12. And so there's your number of outcomes. All right, let's check out this problem. Now, this is my favorite problem when talking about permutations, because when we talk about permutations is when the order matters. And does it matter what place you get in or what order you come in a race? Yeah, I mean, first place is different than third place. Everybody wants the first place, they don't want the third place. It's different. So, let's take a look at this. I'm going to ignore the word podium here for a second. And let's take a look at our 5 racers. So here are our 5 racers right here. The dude with the small arms, that's actually the brother of the dude with the long legs and the small arms. His name is T-Rex. And then we have Bigfoot right here. So they got the Bigfoot. Spiky hair, confident dude, raising his hand. Oh, is that you, Schneider? Okay, then we have Skinny Head. No, I think that's you right there. No. So, if we had 5 racers, how many different ways can they finish? How many different finishes can there be? So how many places are there going to be when they finish? There's going to be 5, right? We'll have first place, which is actually the first event. So first place. We have second place. There's third place, fourth place, and 5th place is right there. We totally ran out of space right there. That's okay, we'll move this down. Move that down just a little bit. Okay, so we got 3rd place, and 4th, and 5th. This is almost like the last problem. It is a permutation. How many choices do we have to get first place? There's 5 choices. Okay, and then let's see. Bigfoot finishes first because he has that advantage. So he's gone. And then we have second place. How many options are there for second? 4. And then let's see, who's gonna finish next? Skinnyhead. Skinnyhead finished next because he couldn't see the Bigfoot that was distracting everybody else. Now for third place, how many options are there? 3. And then for fourth place there'll be 2 and 1. You guys see the pattern? This can also be written a different way. It can be written as 5 factorial. You see that exclamation point? That's not an exclamation point. That's factorial. Factorial. And if you guys check out your calculators, it's also in your calculators. Look for the button that says PRB, that stands for probability. You'll find factorial in there. Press the number 5, then press factorial, and press enter. See what you guys get. So after you multiply all this together, you should get 120. Now, isn't that crazy when you sit down and think about it? There's only 5 racers, and there's 120 different ways that they can finish. That's pretty crazy when you think about it. It gets even crazier when we don't ignore the word podium. How many finishes are there with podium? There's 3 finishes. Okay, let's get our other 2 racers back up there, because the podium spot only has 3 places to finish. So there's not 5. There's only 1, 2, 3, because we only have first, second, and third. All right. So this time, how many choices do we have for first place? Oh, it's still 5, right? And then how many choices do we have for second place? 4. And then the third place there'll be 3 choices left. And so for just figuring out how many possible podium finishes, we have 5 times 4, which is 20, and then we multiply it times 3, that's going to be 60. So there's 60 different podium finishes, which is still, like, in my opinion, that's a lot of different finishes that we can have just having 5 players. Isn't that kind of crazy? Come on, that's crazy. All right, now let's look at different ways we can write, different ways that we can write the permutation. Okay. Permutations as a formula would look something like this. There's n right there and there's an r right there. A permutation is the same as saying n factorial over n minus r factorial. Now, what does that mean? Well, let's take a look at our problem and see if we can make it make more sense. Our problem says that there are 5 different choices, and there's only 3 spots. So, so when we're doing this, the n would be your choices, like total possible choices, and the r, that would be the events. How many events are there? See, for the podium finishes, there's 3 events. There's 1, 2, 3, because there's 3 spaces. Or 3 places for them to get. So we're doing 5 permutation of 3. And let's see what that looks like when we start plugging in the numbers. So this equals, well, we have 5 factorial, which kind of makes sense, because see right here, it's almost 5 factorial. It's 5 times 4 times 3. It's just missing the 2 times 1. So how do we get rid of the 2 times 1? Well, that's when this part comes in. We want to take out the 2 times 1. So we want to take out 5 minus 3 factorial. What is 5 minus 3? What 5 minus 3? That's 2 factorial. That's 2 times 1, isn't it? So like if I were to write this out, it would look like this. On the top, you would have 5 times 4 times 3 times 2 times 1. And the 2 and the 1, that's what we want to cancel out. And on the bottom, we have 2 times 1. Oh, check it out. We could cancel them out now because when we divide them, they're going to be just 1. And so that's how you get 121, writing it with permutation notation. Thank you, Curls, for telling me I did the wrong answer. That's 60. Oh, you crazy math teacher. Don't even know how to multiply. Hi. Okay. Now, what about problems like this? Now, these problems are gnarly cool. How many different ways can we arrange these letters? How many letters are there in this word math? There's 4 letters. Now, we can sit here and list them out. Math. Mat. Wait, that totally did it wrong. Mat. And then we can go ta. And we could do tha. Right? I mean, we could go on for a long time here. Another way you can do it is by using the counting principle, which we all know and love. How many events do we have here? Let's see. 1, 2, 3, 4. We have 4 events. 4 different times when we have to choose something. That's how you know there's 4 events, because we have to choose a letter for the first one. How many choices do we have for the first event? Well, how many letters do we have to choose to go in the first spot? There's 4 of them. And then how many do we have for the second spot? How many? There's 3, because there's -1 from the first one. And then for the third spot, how many choices do we have? Then we'll have 2 choices. And then finally the last one, we only have 1 choice. And that looks kind of familiar. What's a different way we can write that? 4 factorial. Okay? Now this works out pretty well for this problem, because it says how many different ways can you write it? And we'll come up with that many different ways. So what is 4 factorial? 4 times 3 is 12, times 2 is 24. So this equals 24. There's 24 different ways. Sometimes you see the word distinguishable. Distinguishable. That means different. Distinguishable ways. Oh, that looks really long. I hope I spelled it right. It looks, distinguishable. So let's take out this next word right here. I'm going to rewrite this word. I'm going to rearrange 2 of the letters. So we have, let's see, and the E and the S. All right, you guys see the difference? What do you mean? I switched 2 of the letters. Yeah, I did. I switched the Z's. The Z's got switched. Now, are these distinguishable? They are not distinguishable. They're not different. They're not different. So we gotta take that into account. We can't just say, what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. You can't just say 9 factorial. You can't just do that, because some of them, when you switch them, it doesn't change it. It's not different. So how are we going to figure out how many different ways we can write this? Well, all you have to do is you have to divide out those doubles. So here's a double. We got to make sure we divide them out. And this is how you do it. You find a letter that's doubled. So Z is doubled, right? Or is more than 1. So because there's 2 Z's, we write 2 factorial and we divide the 2 out. Are there any other letters in there that have more than 1? Yeah, there's the I's. The I's are repeated twice. And so we put a 2. Now, if there were 3 I's in there, then we would have 3 factorial. But it's there's not 3, there's only 2. And so now you just have to go 9 factorial on the top and divide that by 2 factorial. Well, 2 times 1 times 2 times 1. And so it's 9 factorial divided by 4. Do you guys know what 9 factorial is? It's a ginormous number. Take that number divided by 4, and you should get something like this. 70,000, what? 70,000. No, 9,000? 90,000. I knew there was a 7. 720. And that's how many different ways. That's crazy, right? 9,000, man, if I had $9,000 in my pocket, that'd be really cool. Different ways you can rewrite these letters. 9,000, 90,000, that's crazy.